All right. So today we're going to be discussing integration. Mm, Integration. There you go. By parts. And it is another in the long line of methods that we will use to do integrations. Again, as you well know, we need to find the integral of f of x dx from a to b. And that's great. And of course, it's going to be this f of b minus f of a. Any idiot knows this. The hard part is finding the antiderivative. Okay? So we talked about substitution when you've got a function in a function. That's great. Well, today we're going to look at integration by parts, and that happens when you have, well, a function times a function. And you're like, well, can I use substitution? Well, if u is x, then du would be dx. You still have a u, it would be the same thing. So, no. But I see a product. Whenever I see a product, my first instinct is always, is one of them a derivative, sort of the other one? For instance, we did this last week. We had 5, I don't know, what do we have? 5x e to the x squared or something. You're like, wait a minute now. This is a function in a function, right? And the derivative of that is sort of that. That's a substitution rule. But today, that's not true here. So what we do is this. Now you might recall back in Calc 1, if you add some f of x times some g of x, and you take the derivative of it, of course you get f prime g plus g prime f, which is the product rule, yes? Well, this is very similar to that, except that we're working it backwards. And so what we're going to do, if I can find my eraser. Oh, wait, no, I forgot. It's on this deal now. I was recording this week with my other old setup, and I've kind of forgotten how to run this one. So what we're going to do is we're going to have a u and a dv. And you're like, what? Just go with me. Just freaking go with me, yo. So what we're going to end up with over here is we're going to have an integral always of a u times a dv. And we're going to choose one of these guys, either the x dx or the sine x dx. One of them is going to be our dv, and one of them is going to be our u. Okay? And then we know that from now on that the antiderivative of that thing is always u times v minus the integral of v du. And it's just a simple little recipe. That's all we got to do. Well, once you find u, then obviously du is pretty straightforward. You just take the derivative to get to here. And if you know the derivative, all you do is take the antiderivative to get to v. And then again, it's just u times v minus v times the derivative, or the antiderivative of d, or v times du, and take the antiderivative of that. So then the question simply then is, well, who should I choose to be which? Does it matter? And the answer is, most of the time, yes, it does matter. And so there is a little acrostic, if you like. These are the orders in which you should always choose your u. If you have any logarithm functions, for goodness sakes, make them u. Because if you made them dv, you'd have to antiderivative a log function, and nobody wants to do that. Secondly, inverse trig functions are also very hard to antiderivative, but they're not very hard to take a derivative of. Algebraic functions, things like x squared, things like x cubed, things like whatever, e to the x, well, that's e to the x exponentials. Trig functions are next, and then, of course, exponential functions. If you can't antiderivative e to the x, you've got issues, right? So, pretty easy to do. So when I look at this deal here, I'm thinking to myself, now wait a minute. X, you see, is an algebraic function. Algebraic comes before trig. So I'm going to let x go here. And sine of x dx is going to go right here. Now, it's important to note. The other reason we do it this way is because when you take the derivative of this algebraic function, it goes away. That's nice. It's very nice. From whence did sine come? It came from negative cosine. Yes? So, the recipe simply states you take negative x cosine x minus, always minus, the integral of v du. And you're like, well, that's cool. Can I pull that negative out? You can. So of course it makes it this. And from where did cosine come from? Well, of course it came from sine. So this piece out here just keeps coming down. Now I'm going to antiderivative this thing. And where did it come from? Sine x plus c. And of course, a person could always check themselves to give it to me. Why aren't you giving me there you go. If I wanted to take the derivative of this, it'd be the derivative of that, which would be negative 1 cosine x, plus, and it would be negative x times the derivative of that, which would be minus sine x, right? Plus, and what's the derivative of that? Cosine x. Dude, this and this cancel out. Shut up. This is just x sine x. And of course, the derivative of that's 0. So this thing right here is my answer. Yay, it works. And it's not terribly difficult. Here's another one. You're like, well, this is cool. We can do this 100 times. We can. Nobody wants to, but we can. And so again, u will be my algebraic function this time. And of course, this is 1/2 e to the 2x, right? Now, the recipe, again, is just uv minus the integral of v du. So it's x squared over 2 e to the 2x minus the integral of, it's a half times 2 is 1. So it's x e to the 2x dx. And you're like, dude, that's also a product. I get to do this again. You do. So there it is. And then du would be what? Dx, of course. And then dv would be e to the 2x dx. And then v would be a half e to the 2x. And then this first part just carries down. And the negative's still here, so don't lose it. It's a pretty common mistakes people will do because they're not paying attention. That's v, it's u times v, minus the integral of v du. Well, that's cool. Yeah, it's pretty hot. Because now, if a person distributes that negative through, negative is a positive. Now I get to integrate this guy. We already know what the antiderivative of that is. It's x. It's going to be another half, so it's going to be a quarter this time. Ta-da! There's my answer, man. It's pretty cool, pretty easy to do, not too difficult at all. You're going to see some other ones that are going to kind of make you pull your hair out. Won't lie to you, this is not a very fun one to do. This is one where you're like, oh, wait, Mr. Groom, what did he say? Mr. Groom said is liote. So trig comes before e to the x. So the derivative of sine is the cosine of x dx. And then, of course, this is e to the x dx. And the antiderivative of e to the x is e to the x. So our answer will be e to the x sine x minus the integral of e to the x cosine x dx. Ah, geez, I got to do it again. So this time, let's let u be cosine. So du would be negative sine. So uv again. And it's this times this. There's another negative here, so I'm going to bring that out. Oops, there's an e to the x, dummy. Now, allow me to make this, so remember, this is what we were trying to find. We were trying to find this guy, right? So it's still on the other side. This is what we're trying to find the derivative of, or the antiderivative of. So let's distribute this negative through. And you're like, dude, we got back where we started from. I know. Wait a minute. How are we going to finish? Listen. If you've ever been to the fairgrounds and you rode on a little merry-go-round, and here's Mom. She's standing over here. Okay. Looking frazzled because her baby's on the merry-go-round or something. Or maybe she's happy that you're on the, I don't know. But once you've gone around one time and you've seen Mom, hey, get off the merry-go-round. For God's sake. It's the same. You're just going to see the same thing again and again and again. These guys are never going to go away. E to the x and sine x is just going to be circular, just literally going around and around again and again and again. Get off the merry-go-round. So watch what I'm going to do. I'm going to add this to both sides. Can you do that? Literally, if you go back in time and think back about the cardinal rule of algebra, whatever thou doest to one side, thou must also doest to the other side, right? King James Version. Right? And so you end up with this fella. But that's not what I wanted, Mr. Goom. I only wanted this part. Well, good. Then divide by 2, weirdo. Ta-da! Ta-da! Plus C. Bam, yo. Bam. Oh, you don't like it like that? Well, then you put the half in front. Oh, you're fractophobic? Then put that 0.5 there. That's key. Do whatever you want, brah. Bam. Ta-da! Well, why did you get 2 cosines? That's cute. There we go. Got it? Great. Hey, let's do another one. Stream, you literally could do these all day long if you want to. Pretty much. Wait a minute. What if I had x ln of x? I know what you're thinking. That doesn't look fun. Wait, the acrostic literally starts off with ln for log, yes? So then du would, of course, be 1 over x dx. Hey, that's key. That means dv is x, which means v is x squared over 2. Interesting. So u times v, right? Minus the integral of, now it's this fella times this guy. Now notice, it's going to be just x over 2, yo. Right? Because this x and one of those is going to cancel. There you go. Dx. And then if you distribute it out, or if you antiderivative that, you will get the following. X squared over 4. Huh? I think so, bro. Mr. Grimm, are you sure you're right? No, but we can take the derivative and see. Take the derivative of this, you're going to get 2x over 2, which of course is just x, ln of x, right? Right? Plus the first times the derivative of the second, which is that mess there, minus 2x over 4. Wait for it. Cancel, cancel, 2. Cancel, cancel. Ooh. X over 2 minus x over 2 is whoosh, gone, and you're left with, dude, x ln x, yo. Pretty tight. Okay. Oh, we can do these all day long. Let's do another one. Oh, I know. Let's do this one. Yeah. Oh, yeah, yo. Yeah, sure. Why not? But that's gross. You're not wrong. So let's let u be the arctan, because no one wants to integrate that. We'd rather just take the derivative of it. Of course, that's 1 over x squared plus 1 dx. Am I right? Oh, I'm going to die. There we go. And, so we may have run into one that we cannot do because we don't know enough going further from here. But we'll play it by ear and see what's up. So we're going to get x squared over 2, arctangent, minus the integral of, pull a half out front if you don't mind, it's x squared over x squared plus 1. And we don't know how to solve that yet. We will learn this baby later on. You're like, Mr. Groom, what do we do if we see one of those? Well, you won't on the homework because one of those won't be on there. Today's lesson anyway won't be on there. We may come back to this. You know, I'll say something to somebody like, I don't know, Lily, remind me when we do this in a few days. Lily, when we get to the part where we have to do long division to simplify, remind me. Oh, what the heck, I'm going to do it now. Notice that the numerator is x squared, the denominator is also x squared. We cannot have that. That is not bueno. So what we're going to do is we're going to do long division. But I suck at long division. But Mr. Patterson never taught us long division. Grow up. Just grow up. How many times does x squared go into x squared? It goes in one time. Duh. And when it does, what do you get? Well, you're going to get x squared plus 0x plus 1. And you minus, and you're going to get 1, and you're going to get minus, well, you have a remainder of negative 1. So what you're going to end up with is you're going to end up with this part right here can be rewritten as okay, 1, that's this guy right here, minus 1 over x squared plus 1. Well, now wait a minute. If I'm integrating this whole shebang, what can I do? Well, it feels like I could do each piece individually, correct? Am I right? I think I'm right. I think so too. So, what's the antiderivative of 1? Well, it's x, Mr. Groom. I know. That's key. And I'm going to distribute that negative a half while I'm at it, okay? Hey, what is the antiderivative of that? Isn't it arctangent? I think it is arctangent. Good call. So it's a half, because it's negative and a negative is a positive, arctangent of x plus c. Now I can see some of you, Lacey, don't believe me that this is the true antiderivative. Well, let's find out. Product rule. So it's going to be 2x over 2, which is just x, arctangent. That's Q. And then plus x squared over 2 times 1 over x squared plus 1, which is disturbing, minus a half. And the derivative of this is plus a half, and then it's going to be 1 over x squared plus 1. And you're like, that's so gross. What do I do? Well, feel like we need a common denominator here, don't we? So this is x squared over 2x squared plus 1, right? That's what this piece is. And then here I want to have a common denominator, so I would need to have an x squared plus 1 on top, and I need to have one on the bottom as well, correct? Right? And then plus, and then this is a 1 over 2x squared plus 1. That's tight. Don't forget to distribute the negative through here and here, so this ends up being negative x squared, so x squared minus x squared is 0. Here's a negative 1 and a positive 1. That is also 0, meaning that all of this garbage cancels out. Ta-da! And there's your answer, friend. Okay? Now, the next one I want to do is, and we will see more of these as time goes on. And after a while, you're just going to be able to see them like literally a mile away and go, oh, I know what to do. Okay, friends. We did one of these earlier. We did one earlier with an x squared in it somewhere, didn't we? We did. And we did it with an x. And you see how the x went away after one derivative? That was cute. I liked that. That was nice. And we did another one where we had an x and it went away after 1. And somewhere I did an x squared, I swear. I swear I did. There it is. And notice how we had to do it twice with x squared? How many times do you have to do with x to the 4th, you suppose? Just take a wild stab. Probs 4 times. You're not wrong. But you can see where this is going to happen. It's going to go away. So what we do when this happens, and there's a bunch of them, what we do is we just do a whole line of this. And the reason for this will become pretty obvious momentarily. And I'll show you where I'm talking about. And the antiderivative, and the antiderivative, and the antiderivative, and one more time. Why one more? Well, I'm going to show you right here. Glad you asked. Nope. 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 There. Haha. Listen, friend. Notice how we had an x squared and then our du is this x function? And then notice how that du became the u for this one? Huh? Now we took the 2 out, but come on, let's be honest, right? We just kept taking the derivative until it went away, didn't we? And in this column, we just kept integrating, didn't we? And it was always, look, u times v, right? And then it was u times v. So we're going to need to have, another v, in other words, in that next column over. What this is called, and this was learned to me after college. I don't think I learned this in college. I think I always do it the hard way. This is called the tabular method, which is pretty cool. Just a pretty fun way of doing it. And what you do is you line them up, and then you just go on the diagonal. So skip the first one. So boom, 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 boom. And notice, check this out, it's plus, minus, plus, minus, plus. And so my answer is literally x to the 4th, e to the x, minus 4x cubed, e to the x, plus 12x squared, e to the x, minus 24x, e to the x, plus 24, e to the x, plus c. Done! And you're finished. Well, I want to do it the hard way. Good for you. So if you want to do it the hard way, again, this only works nicely when you have a algebraic function here, which will go away eventually. Okay? If that's true, you're good to go. If this was e to the x and sine x, what are you doing? It ain't going anywhere. And so you would end up with, again, x to the 4th, e to the x, minus the integral of, and then I want to bring the 4 out front. Well, good for you. Good for you. Right? And you take the antiderivative of that, well, you let u equal x cubed, but you could see it could be 4x cubed, right? So then du would be 3x squared, or again, could be 12x squared, which you have above, dx. And then dv is what? Is e to the x, obviously, and v is e to the x as well. So here it's going to be x to the 4th, e to the x, minus, and then it's going to be 4. Now check it. It's going to be minus 4 times this, so it's 4x cubed, e to the x, right? Minus, but remember, this negative 4 is times by everybody, right? Right? Right, Mr. Groom. So if you distribute that negative 4 through, you end up with this. Right? Right? I feel like that's right. So play it again. And you can pull that 12 out if it makes you happy, or don't if it doesn't make you happy. I don't care. Listen, I'm happy either way. Whatever makes you happy makes me happy. It is for the children after all. That's why I do my job. Right? I mean, where would we be if it wasn't for the children? X to the 4th, e to the x, minus 4x cubed, e to the x, plus. So it's plus, and then inside here we're going to have, of course, 12x cubed, squared, e to the x, right? Because that's this times this, minus the integral of that times that. So 24x, e to the x, dx. Good grief. One more time. Let's let u be 24x. Let's let du be 24 dx. Shut up. dv is... I'm tired. And so, of course, it's x to the 4, e to the x, minus 4x cubed, e to the x, plus 12x squared, e to the x. And, of course, it's minus whatever we get here. So it's going to be 24x, e to the x, minus the integral of 24 e to the x dx. Okay? Doesn't take a rocket surgeon to see what's going to happen to that. Plus 12x squared e to the x, right? Minus 24x e to the x. Negative, negative, positive 24 e to the x, because that's the antiderivative of that, plus c. Ta-da! But the tabular method is so much nicer on that problem. Okay? Again, only works when one of them is an algebraic function like x to the 4th, which will go away at some point. Okay? Other than that, bam, there you go. So again, to top off, let's go back. This is the recipe. That's it right there, friends. That's it. And Liate. Pay attention. This is how to choose you. Hope that helps. Good luck to you.